Figure below shows the cyclic process for 1 mole of monoatomic gas in a heat engine. Given that V1 equal to 3 liter and V2 equal to 6 liter, and state 1 changes to state 2 through an isothermal process. Find the thermal efficiencies of the heat engine. The graph given is the P versus V graph, where the P is a Pascal in Pascal and the V is in meter cubes. The state number 1 and the state 2, they are lies on the same isotherms, because from 1 to 2, state 1 to 2, the process involved is an isothermal process. Therefore, state 1 and state 2, they are lie on the same isotherms and the temperature are the same. Now we can sketch another isotherms through the state number 3. Since this isotherm is located at the left of these isotherms that connecting the state 1 and 2, then we know that the temperature of the state 1 and state 2, which are the same, is higher than the temperature of the state number 3. Therefore, we have T1 equal to T2 and larger than T3. Based on the result of the comparisons of the temperature for the 3 states, now we can look at the 3 processes that happens between the 3 states. The first one is from the state 1 to state 2. This is the isothermal process, because state 1 and the state 2, they have the same temperature as mentioned before. So this 1 to 2, this is the isothermal process, and this curve we call the isotherms. When the state change from 2 to 3, this process happen at the constant pressure. That's why the process is an isobaric process. And because the volume is reducing, so it is a compressions. Therefore, we call this process as a isobaric compressions. And if we consider the effects on the temperature, then we can see from our result that we analyzed before that the temperature is dropped when the state change from 2 to 3 through this isobaric process. Therefore, this process also we can call it as isobaric cooling. From 3 to 1, the volumes of the gas remain the same. So this process we call it as the isochoric, and the temperature of the gas when it changes from state 3 to state 1, it is increasing from the T3 change to the T1 based on this relationship between the temperature of the state 1, state 2, and state 3. Therefore, we know that this process is isochoric heating. The questions require us to find out what is the thermal efficiencies of the heat engine that is represented by the symbols eta. By definitions, this eta is equal to the output work divided by QH. That means we need to find out this answer, we need to analyze for these 3 processes what is the work done involved in these 3 processes, and also we need to analyze for these 3 processes what are the heat transfer that happens, that take place in these 3 thermodynamic processes. To do that, we can apply the first law of thermodynamics to find out what is the W, work done, what is the Q for each 3 processes. We start from the process when the state change from 1 to 2. That means which is the isothermal process, because from 1 to 2 the temperatures doesn't change. So we know that this internal energy change when the state change from 1 to 2 is equal to 0, because the internal energy of the gas is depends on the temperature T. So if temperature remain the same, therefore the internal energy of the state for the state 1 and state 2 also remain the same. So delta E TH equal to 0. And since this is the isothermal process, the work done we can calculate by using this formula, which is nR T2 ln V2 over V1. Now, of course, this T2 and the T1 is the same. So here we choose to write it as in terms of the T2. There's the reasons because there's the reasons why we choose T2 instead of T1. But the reason would be becomes clearer in our analysis later. And this work done will take the positive value because it involves the expansions of the gas. So it is a positive value. So from the first law of thermodynamics, then we can know that the Q will be equal to W because the internal energy change is 0. So Q will be equal to W, and it will take also the positive value simply because the W itself is a positive value. So the Q involves the heat transfer in the process of the 1 to 2. The heat is transferred into the system, into the gas. From state 2 to state 3, this process happens at the constant pressure. So delta P equal to 0, and we call this process as isobaric. For the isobaric process, the work done is equal to P delta V, where the P is a constant. So here now we take this P2. In fact, we can also choose the P3, but now we choose the P2. And the change of the volume is V3 minus the V2. So this V3 minus V2 will give us the negative sign. Therefore, the work done for this process would give us the negative work done. And the internal energy change also is a negative value because when the state change from 2 to 3, the temperature is dropped. When the temperature drops, it implies that the internal energy change also would reduce. Therefore, the internal energy change will be will take the negative value. So based on the first law of thermodynamics, where the Q is equal to internal energy change plus the work done, and because these two terms both are giving us the negative value, therefore the Q in this process must also take the negative value. Means that in this process the heat will flow from the gas. And when the state change from 3 to 1, this is the isochoric process, because we know that from the graph we can see that there is no change of the volume. So this is isochoric process. For isochoric process, the work done is equal to 0 because the work done for thermodynamic process, if it is plotted in the PV diagram, then the area of the graph will give us the work done. And since from 3 to 1, this line joining the state 3 and 1 is a vertical straight line, that means there is no area on the graph, so work done is equal to 0. And internal energy change, we can get it from the formula of NCV delta T, where the CV is the molar specific heat for the gas at the constant volume. N is the number of mole, delta T is the change of the temperature. When the state change from the state number 3 to state number 1, the temperature is increased. That's why there's a delta T here. And since the temperature is increased, therefore this change of the internal energy would give us the positive value. Again, from the first law of thermodynamics, we know that Q would be equal to internal energy change because the work done is equal to 0. Therefore, since this internal energy change is positive, therefore the Q also positive. That means this in the process of the isochoric, the heat is flow into the system. Bear in mind that our aims is to evaluate the value of this thermal efficiency of the heat engine, which is equal to output work divided by the QH. And then from our analysis for these three processes, then we can now see that this output work is equal to the summations of these terms from for the isothermal process plus these terms for the isobaric process and plus this 0 for the isochoric process. While for the QH, we take only the Q that have the positive value. That means we only consider the process where the systems or the gas in the heat engine absorb the heat. So the QH is contributed by the value of the Q, which is the positive value. So for these three, among these three processes, only the isothermal and the isochoric process will contribute to the QH. So we need to sum up these two terms, and we won't consider this one because this one, the Q is a negative value for the isobaric process. It is considered as the QC, not the QH. Now we start to sum up the work done for the process 1 to 2 and 2 to 3 to get the output work. In the questions, the value of the temperature T2 is not given. That is why now we try to avoid the T2, and then what we do is to change this nRT2 into the P2V2 based on the ideal gas law or equations of the state. But of course, this P2 also, the value is not given in the questions. But please note that here, if we change this as a P2, this one also P2, later we can factorize. So we hope that later we can cancel out the P2 when it is divided by the QH. And the remaining symbols in this expression now is all, apart from P2, the remaining ones, the remaining symbols now are in terms of the V1 or the V2. But here also we already changed the V3 into the V1. V1 and V3 are the same. The reason is because we know the value of the V1, V2 given in the questions. V1 is 3 liter and V2 is 6 liter. We try to find out the QH now. QH is contributed by the positive Q in these three processes. So based on our result of analysis, this QH is contributed by the Q in the process of 1 to 2 and also the process of 3 to 1. So we have two terms. Due to the same reasons, this nRT2, we have to change it to P2, V2. In fact, these first terms and these first terms are the same. And for the second terms, NCV delta T, we change it to, because the N is take the 1 mole, and the CV takes the value of 3/2R for the monoatomic gas. Therefore, we have this, here we have 3/2R, and delta T is T1 minus T3, because this term is, we get it from the this process when the state change from 3 to 1. So the final temperature is T1, then and the initial temperature is T3. So that's why delta T is T1 minus the T3. Again, because we do not have the informations about the temperature, so now using the equation of state, we change this T1 into P1 V1 over R. And this T3 will become P3 V3 over R based on the equations of the state. Bear in mind that we already take the value of the N, number of mole, as 1. Now, this R and R can be cancelled. So the terms in the bracket now becomes P1 V1 minus P3 V3. But This P1 V1, we express it as the P2 V2 based on the isothermal process between the state 1 and state 2. Since this is isothermal process, it obeys the obeys the Boyle's law. Therefore, P1 V1 can be substituted by the P2 V2. And here, this V3, based on the same reasons as this, now we change this V3 to V1. And the P3, this P3 is the same as a P2. So we change this P3 to P2. Therefore, now these expressions can be simplified to this, where we have factorized the P2 here. This is here also got P2. So that means now we can see clearly that if we substitute this output work and this QH into these equations or the formula for the efficiencies of the heat engine, the P2 all would be cancelled out later. Now let us do the substitutions and start to evaluate the efficiency eta for the thermal efficiencies of the heat engine. So we have these expressions. After cancelling out the P2, 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 and then we will have these simpler expressions in terms of V1 and V2 only, without any pressure for the three states in the graph. And take note that the first terms in the numerator and the first term in the denominator, they are the same. We start to substitute the value for the V1 and V2 using the value given in the questions, where the V1 is equal to 3 liter and V2 equal to 6 liter. Then we'll have these expressions. Take note that we don't convert this liter into the meter cubes. We do not need to do that because the liter and liter, the liter in the numerator and the liter in the denominator will be cancelled. And the answer we obtain is equal to 0.1338 or equivalent to or approximately equal to 13.4%. This is the efficiencies of the heat engines, eta, 13.4%. We solve these questions by using the eta equal to output work divided by QH, this formula. But in fact, this eta, the thermal efficiencies of the heat engine, also can be evaluated using another formula, which is equal to 1 minus QC over QH. In our discussions, the QC and QH, we already know which process it contribute to the QC and which process contribute to the QH. So that means if we use these formulas to evaluate the eta, we should get the same answer. So it is worth to try to solve the same problem by using the difference method, and it should give us the same answer.